Welcome to Working with an ANOVA problem. Our problem is subjects must press a button when they hear a signal. The three treatments are three different intensities of the signal. That's these right here. So here's signal 1 and its intensity, signal 2 intensity, signal 3 intensity. The time elapsed between presentation of the signal and when the button is pushed is recorded in hundredths of seconds. So with signal 1, there was a 35 hundredths of a second delay before pressing the buttons, a 24 hundredths delay, and so forth. Samples were obtained by a randomized experiment. We want to test to see if at least one of these means is different at a 0.05 significance level. So it's time to get in here and work on calculations that we've learned about in class. Well, the first thing we need to do is some of the easy things, getting the sample mean. In Excel cell, you'd go into the cell you want it in. You hit the equal sign, and in Excel it's average. Average is the mean. So I go for the average, and I say 35, 24, 28, and 21. And that would be the average of those. And I could get that for each of these. Now I could do the same thing I did there, or I can pull this down and we'll get the averages, and I could calculate them just like that. So if you go into this, it's averaging, and we can look at it, it's averaging those for elapsed times. So these are, shortcuts and ways to get around in Excel. Sample standard deviation. So I want sample, not population standard deviation, but sample standard deviation. So I'd use that, and I want it of that data group, the first intensity. And so I have my standard deviation, and once again I can just pull it down to copy that formula to each of these other cells, or I could have done the same formula for each, but this is a faster way to do that. My sample size, well, we know all of these are 4. I'm just typing 4 in there because that's easier. That's the easiest way to do that. Now, to get the grand mean, remember the grand mean, I have to add up all of these and divide by how many I have. I have altogether 12, and I take all these. So how would I do this? Well, I'm going to say the grand mean equal. So I'm going to kind of just merge this in here. And so now I've got, I'll get the calculation for this. So I say grand mean equal. And how would I do that? I could take the average. So I'd say equal average. And then I put in the data points that I want. Those are the data that I want the average to. And so the average would be 20.083333 or 20.08. So I now have the calculation for the grand mean. Check all the conditions. Now I know that I have a simple, that it was a randomized experiment, that the samples are independent of one another. In fact, we have different intensities. But now I have to check for normality, and because these sample sizes are so small, we're going to use that residual. We're going to look at the normal probability plot of the residual. But how do we get those? Well, let's look for that. Let's look how we can do that. So remember, we got to go in each of these. So I have to take, we're going to take 35 minus 27, 24 minus 27. We're going to get those residuals. So I'm going to take each of the sample mean, subtract it from each of these data values. Then I'll take this sample mean of the second sample and subtract it from each of its data values, and so forth. So the way I would do that is I would say this equals that minus, minus, and then I want to do this one, but I want to make sure that doesn't change when I copy this calculation through. So the way you do that, the way you keep that value to be steady at 27, you put $sign before the letter and $sign after it. So that's that. So now I can pull this all the way through, and I will now have 24 minus 27 gives you 3, 28 minus 27 gives you 1, and so forth. And now I can pull these and get it for the other treatments, because now that pulled to D but line 10, but I kept, the only thing I have to change is I don't want to keep it D9. I want to keep this at 10. Because Could have been a big mess up, and now I have to change all of these. Which will mean I'll have to change this one here too, because I've got to change that not to 10, but I want 11. And then pull it all the way through. So now I've got my new, my residuals for each of the different treatment groups. I can do a probability plot of these data values in Minitab. So I'm going to copy all of these residuals, and now I want to plot them. Now I've got them, but I want to do a probability plot of all of these, so I've got to stack them in one column. So what we do is we take our data, stack columns. So I want to take this, this, all the way to there, and I want to put them in column 1. So all of them come into one column. And now I can do the probability plot on there. So I want to graph, do the probability plot of C1. And these are those residuals. Looks pretty good. Nothing looks too outrageous. And then let's just make sure sample sizes are small. We'll look at the box plot. And remember, this is the distribution of residuals. So now I can put these into my paper, or if you're going to turn this in to show, hey, yeah, everything turned out looking okay. So we'll do our probability plot, make it nice and small so that we can see it. And now we can copy and paste our box plot. So we see that our residuals, there are no major deviations from normality, no outliers, life is good. Now, we have to see if our variances are about the same. Is it reasonable to assume that the populations have variances that are about the same? And it is. So it's 6 less than 6.4 doesn't exactly work, but 6.4 is close enough. So we can assume that it's reasonable to assume that the variances are about the same. Once we get that out of the way, the assumptions are met. Since the assumptions are all met, we can now do an ANOVA using the F-test. So we kind of have to remember that table that we learned, the ANOVA table. So we have to get the sum of the squares of the treatment, sum of the squares of the error, sum of the squares of the total. We got to get these degree of freedoms in. So we have to find out all these quantities inside this ANOVA table. So the sum of the square of the treatments. What is the sum of the square of the treatments? Well, we know how to do that computation. So you would say equal our common sample size of 4. And now we have to multiply it. If you remember, we have to take our sample mean and subtract it from the grand mean. So, and then we have to square that quantity. So we have to take our first sample mean, subtract it from this grand mean, and then we have to square that quantity. We add to that the next one. This sample mean minus the grand mean, the grand mean, then we have to square that quantity. Then we have to add to that the last sample mean, subtracted from the grand mean. Oops, I did that before too. And then square that quantity. And now I've got the sum of the squares of the treatment. Now I have to get, what's our degree of freedom? Well, k minus 1, we have 3 populations minus 1, so that value would be 2. I can just put that right on in. And minus 1, well, we have a total of 12 minus 1, that would be 11. So I can change that to 11. And then n minus k, 11 minus 2 is 9. So I've got my degree of freedom. Now what I have to do is I have to find the sum of the square total. Remember, because we have that calculation that we saw in the notes that I gave you. So the way we do that is we take, in our sample 1, a data value, we subtract it from the grand mean, square that, and we do that for each of the data values. So after you put all these in, we take each of these, subtract it from the grand mean, square it, add them all up, you get this sum of the square of the totals. Now to get the sum of the square of the error, well, we know our calculation. The sum of the square of the error is going to equal the sum of the square of the total minus the sum of the square of the treatment. So there's my sum of the square of the error. I've got my degree of freedom, and now I can calculate the mean square of the treatment. That would just equal the sum of the square of the treatment divided by the degree of freedom. Now to get the mean squared error, I put my equal, it's the sum of the square of the error divided by the degree of freedom. And to get my F statistics, I just divide these two. And I got my F statistic. Now I could go in here and further do a few things. So I can look at what my critical value would be, and then what my p-value would be. So now I can find my critical value and my p-value. To get my critical value, I'd have to look at my, remember how I would do this, I'd have to look at my degree of freedom of the numerator, degree of freedom of the denominator. I go into my stat book, in the back of the stat book, for my F tables. And I'll try to make sure that I can get these F tables to you. So again, my degree of freedom in the numerator is 2, and the denominator, it is 9. So our degree of freedom of 2, the numerator, the denominator is a degree of freedom of 9, and we're doing this at a 0.05 significance level, so the critical value so 2 go all the way to 9, 0.05, the critical value is 4.26. The p-value, in order to find the p-value, I could go into Minitab and find it, or I could try to look once again at my book, the table in the back of the book, and again, degree of freedom of 2, then 9 degrees of freedom in the denominator, and I'm trying to look up the test statistic, which I got as 7.6. So it's somewhere in between these two right here. So my p-value is between 0.01 and 0.05. So we could capture our p-value, or we can use Minitab to find that p-value. So we go into Graph, Probability Distributions. We want to view the probability. First we have to pick the distribution. It's our F distribution. Degree of freedom in the numerator is 2. Degree of freedom in the denominator is 9. And we want to find the probability, given an x value, to the right, so the right tail where my x value is 4.26. Excuse me, 7.61. And we find that it's got a p-value of 0.01162. So the p-value, the exact p-value, very small. And it is in between. It is between 0.01 and 0.05. So very small p-value. So doing this at a 0.05 significance level, both our p-value tells us that it's less than 0.05, we're going to reject the null hypothesis. And if we did the critical value method, so we see that our p-value, so our p-value 0.0116, it truly is less than 0.05. So we reject the null hypothesis. And also we could have done the classical method. Since this is like a right-tailed test, we want our test statistic to be greater than our critical value. Our test statistic is 7.61. That is in fact greater than our critical value of 4.26. So even using the classical, obviously both of these methods would tell us to reject the null hypothesis. So at a 0.05 significance level, there seems to be a difference, at least in one of the mean times or time elapsed between signal and button. Now that we've rejected it, how can we find out which one it is? Now, without showing how the Tukey works, I'm just going to show you using Minitab how you can tell. So I'm going to take this data right here. So I can go on and I'm going to do my ANOVA procedure. They're in different columns. I want to keep it at that we have equal variances, 95% confidence, and I want to do my comparison. I want to do a Tukey. I hit OK. And what I find, there we get our F statistic, 7.61, like we got, a p-value of 0.012, which is we got it more exact as 0.0116, but that's 0.012. So when we look at our Tukey results, look what happens. It's telling us signal 1 is kind of in a group all by itself. Signal 3 and 2 about have the same mean. So we would say the different mean would be signal 1. That's basically how you work an ANOVA problem.